Well, good morning. In today's class we continue with nozzles. First I will review what we have done so far, and then we will see whether there are any gaps, anything which has happened in nozzle development which I have not covered, and those things we will cover. Having said that, what did we do about nozzles? We told ourselves it is something like a vent, and we first learnt how to calculate the jet velocity, right. How did we calculate? We said I have a chamber which is at the pressure Pc. Suppose at the exit I have a pressure Pe, I can calculate the jet velocity 0.1. Then we told ourselves, look here, I want Vj to be as high as possible, and to be able to get a high value I need this vent or opening to be in the form of a convergent divergent shape. And we also put a condition that the minimum area which we called as a throat should have a Mach number equal to 1. We called this as a de Laval nozzle or a convergent divergent nozzle. In the convergent part the Mach number was less than 1, in the divergent the Mach number was greater than 1, right. After having done this, we said at the exit I have exit pressure which is Pe, the ambient pressure is Pa, and if the exit pressure is not matched to the ambient pressure, I could have something like shock diamonds in the process here, either due to under expansion or due to over expansion. After this we also took a look at what is the flow through the nozzle. In fact, we got an equation of m dot is equal to 1 over C star into Pc into At was the flow, and we got an expression, say m dot by At, let us write it down, m dot divided by At was equal to, if I write this as a chamber pressure Pc into 1 over C star here. C star had units of meter per second, and we were able to correlate the pressure built in the chamber what is the pressure built as a function of the mass flow rate. We call this as a transfer function, or C as the characteristic velocity of a rocket. Let us take one example just to clarify things. Suppose I have a rocket, let us say, let us now presume that I know something, I put propellant in it. The mass of propellant I have in the rocket is, let us say, mp. Let the rocket fire steadily for a period of t seconds, then I know that the mass flow rate through the nozzle is equal to mp divided by t. Let us say mp is in kilograms, this is kilogram per second. If the pressure built in the chamber is Pc, and after all I give a particular throat At, I can directly say that mp by t is equal to m dot p is equal to 1 over C star into the chamber pressure into At. I can determine this value of C star. If I go and do an experiment and determine the value of C star, and then I start comparing the value of C star which I actually measure to the C star which we ideally derived, and how much was it? We told ourselves C star is equal to under root RTC by capital gamma. I find that the ideal value may be a little more than the actual value because some flow losses are taking place. We called it as C star efficiency of a rocket or chamber. We also told ourselves, well, I have divergence, or I have a rocket nozzle something like this, and I can also write the thrust of a nozzle as equal to, in terms of the chamber pressure, in terms of At, and I can put it in terms of a coefficient. We derived the equation for this coefficient, we call this as Cf ideal, and we told ourselves, look here, the thrust need not always be the same. That means always I have Pe here, I have the ambient pressure here, always Pe may not be equal to Pa, but the thrust is a maximum when Pe is equal to Pa. We called this ideal thrust coefficient as Cf0 when the exit pressure was equal to the Pa. Just same way I have a rocket which is firing, I put some measurement here for a transducer. I measure what is the thrust what is generated by a rocket, then I can go and measure the value of Cf. I get the value of Cf which I calculate using the ideal value, which we call as the thrust correction factor eta f. I think this is all what we did. We also did something which was important. We told ourselves, instead of specifying the exit pressure and the chamber pressure, I can also specify a rocket in terms, or a nozzle in terms of the exit area AE divided by the throat area, which is more representative, because this is where the Mach number is always 1. We called it as AE by AT, right. Are there any questions on what we have done so far? Mind you, all what we have done is for an ideal case, an adiabatic nozzle and one dimensional flow. We always said that the flow is going straight like this, right, and all the mass flow rate is contributing to the thrust and expansion. Are there any questions so far? This is all what we have done in nozzle. Yes?
So how do we compare the combustion efficiency with C-star efficiency?
Yes, let's take a look. Your question is, how do we, let me put your question on the board, it's something important.
Why do we go for C-star efficiency?
Why do we go for C-star efficiency? The question which is asked is, why do we compare or club C-star efficiency with thrust coefficient and call this as the specific impulse? This is your question. Let us first clarify, C-star efficiency is something which tells how much chamber pressure is developed when I give a certain mass flow rate through the nozzle. The nozzle is identified by throat area. In other words, the transfer function between mass per unit flow rate through the nozzle or mass flux through the nozzle at the throat to the chamber pressure gives me the value of C star, because we had the expression Pc is equal to 1 over, no, let's put it down, m star m by AT we could get the chamber pressure for a given mass flux at the throat, and this is your transfer function. What does it tell us? What does this expression tell us? And we also had the expression C star gave me something like under root R Tc by the value of capital gamma. It was a function of under root gamma 2 over gamma plus 1 to the power gamma minus 1, gamma plus 1 divided by gamma minus 1. What does it really tell? It tells, supposing I have a mass flow rate through the nozzle, mass flux through the nozzle, what is the value of chamber pressure I get? And what is it we have been telling ourselves all along? To get a high value of Vj, I need a high value of chamber pressure. Therefore, this C star tells you the capacity of whatever you have in the chamber to generate a high pressure. Therefore, C star is not a function of the nozzle performance, but more like how a chamber can build up high pressure. All what it tells you is, let's take one or two small examples. Let's take an example of a rocket which burns. See, we have still not done propellants, that will be what we will do in the next series of classes. Suppose I have a tank containing, let's say, liquid kerosene, I call it as kerosene. I have another tank containing oxygen. I take both these liquids, I take liquid oxygen, LO2, kerosene over here. I take both of them into a chamber, and what is it I have to do? I have to push these things in and I have to generate a high value of Pc. And to be able to generate a high value of Pc, I also plug in some amount of total quantity of M kerosene plus liquid oxygen. I put it here, I allow it to burn, and when it burns I generate a value of Pc. Therefore, C star tells me the capacity of propellants to generate a high value of chamber pressure Pc. That means it is a chamber only. We have not done anything with respect to this, because C star we only looked at the nozzle flow. We told ourselves, well, m dot is equal to rho t AT into VT. Therefore, we never really looked at the divergent part of it, we looked at only up to this place. Therefore, C star is representative of the chamber to be able to generate high pressure gases when some mass is flowing. If instead of having kerosene and oxygen, suppose I have say liquid hydrogen and liquid oxygen, maybe the C star could be higher. Therefore, I would prefer this to this, and C star therefore becomes a capacity of the chamber for a given propellant to generate high pressure gases. Like normally the value of C star is around 2000 to 3500. A lower performing rocket or propellants which are not that good will give me a lower value, propellants which are extremely competitive, extremely energetic will give me a higher value. That is C star. Now, when I look at CF, what is CF? We define CF as equal to thrust is equal to CF into PC into AT. In other words, if I had terminated the rocket at the throat itself, let us qualify this through another example. If I have a rocket nozzle and I terminate it at the throat where Mach number is equal to 1, and now I tell myself I have chamber pressure PC, and now for all practical purposes, now I do a diagram over here in which I say that PC is acting on all these areas, PC is also acting on this area over here, the normal to this is equal to this, PC is acting on this head end over here, PC and the nozzle end is acting, therefore this and this gets cancelled, this and this get cancelled. The ultimate thrust what I get is something, this is unbalanced, this is PC, if PC is very much higher than P, I can neglect it, and therefore my thrust is equal to PC into AT, just an order of magnitude. Now, what I do is I have the divergent part like this, and now I find that the force has somewhat increased because of this expansion, and therefore I write F is equal to CF into PC into AT. Therefore, CF is something like thrust magnification due to the divergent part of the nozzle, and therefore CF is a quality factor for the nozzle. In fact, CF for most nozzles are between 1.2 to something like 3 or 4. We will work through some examples in the later part of this class. Therefore, I can tell you that CF is a quality factor for a nozzle, C star is a quality factor on the capacity to generate pressure in the combustion chamber or in the chamber of a rocket, and the product we derived was the product of CF and C star is the net ISP. And what is ISP? It is the total thrust divided by the mass flow rate. Let us put that down again, because we will expand on it a little bit in the next few minutes. Let us write it out. Force is equal to thrust is equal to CF PCAT, and what did we tell? Well, PC can be written as, in terms of mass flow rate, m dot is equal to 1 over C star into PCAT, and therefore PCAT I can write it as equal to m dot into C star divided by AT into AT, AT got cancelled, and I have thrust or force divided by m dot is equal to CF into C star, and what do we get? Force m dot is equal to mass of propellant into time, F into time is impulse, impulse per unit mass of propellant was what we called as specific impulse of a rocket. Therefore, the specific impulse of a rocket has two things in it: the capacity of the chamber to generate high pressure and high temperature gases, and how you expand the gases to get high velocity. Therefore, let us keep this terminology very clear. I have nozzle factor, chamber factor, which gives me the net ISP of a nozzle. I will dwell on this a little in detail in the next couple of minutes. Let me get started with it, because all of us are now clear about area ratio. But does this answer your specific question? Why C star? Why CF? and what is the relation and how I got the specific impulse. Let us do one example. Let me take the example of, let us say, a particular nozzle which operates, let us say, in vacuum, and let me take another nozzle which operates on the ground, let us say at Chennai, which is at sea level. Let us say I have a nozzle, this is the chamber which generates high pressure, I have the exit pressure is equal to, let us say, PE. At sea level the ambient pressure is equal to PA, at sea level it is equal to 100 kPa, which is equal to 0.1 MPa, right. Now I want you to tell me what is the relation between, let us say, ISP, I want ISP at sea level condition. I say ISP, let me put it a little more clearly, specific impulse at sea level. How do I write it? I write it as equal to m dot Vj plus I have PE minus PA into what? AE momentum thrust plus the exit pressure minus PA into the exit area, where AE is the exit area of the nozzle. Mind you, we derived this, right, and we said we had a control volume and therefore we found a pressure thrust was there. Please check this again, right. Can I go forward? Now I want to be able to say, if I say I am looking at the same nozzle, if instead of it operating on the ground sea level, if it is going to operate in vacuum, what is going to be the difference? Let us say the nozzle now operates under vacuum, the same nozzle, the same area ratio, this is the value, I have PE, I have AE, the chamber pressure is, let us say, PC. If it is going, yes, ISP sea level divided by m dot, very good. No, let us put it this way, let us redo it. F is equal to m dot Vj, therefore the specific impulse is equal to Vj plus Pe minus Pa into Ae divided by m dot. That means I have more than the jet velocity, I have some contribution from this coming. Now I want to find out what is the specific impulse at sea level. Let us rewrite it. Specific impulse at sea level is therefore equal to Vj plus I have Pe minus Pc, no, Pc minus Pa, Pe minus Pa divided by m dot is the value into the value of Ae at sea level. Now what will be the value of specific impulse if the same nozzle functions in vacuum? I call it as vacuum specific impulse. Vacuum is equal to, what will be the value? Pa goes to 0, it is vacuum, therefore I have Vj plus Pe divided by m dot into E. In other words, the same nozzle when it is fired in vacuum gives me a higher thrust because minus Pa is missing over here. Can I relate these two? Let us say ISP at vacuum, I find therefore the specific impulse of a nozzle, the specific impulse of a given rocket operating in vacuum is greater than when it operates on the ground. In other words, the specific impulse corresponding to operation in vacuum is greater than when the same rocket operates at sea level conditions. Now I want you to give me a slightly, let's expand on this and find a relation between the two. Therefore now I tell ISP at vacuum is equal to Vj plus P, what is the value of m dot? M dot is equal to 1 over C star into PCAT, that is in terms of C star, and I have the value of AE here. AE by AT is the nozzle ratio, which is equal to Vj plus I have C star into PE by PC into the ratio, that is the nozzle area ratio over here. In other words, compared to a nozzle which gave me Vj plus this value here, I get a much higher value, and if this particular nozzle at sea level was such that I had optimum expansion, namely P was equal to Pa, the ISP at sea level would have been just Vj alone. All what I am telling is, if the nozzle was such that the exit pressure was same as the ambient pressure, for which we told ourselves the Cf is a maximum, we would have got the value ISP is equal to Vj alone. Whereas the same nozzle, when I fly in vacuum, I get an additional contribution coming over here. Therefore, now the question comes, how do I specify the specific impulse? If I say my rocket is flying in vacuum, I get a higher value of specific impulse. If it is tested on the ground, I get a different value. Therefore, I must be clear in my terminology, and therefore, two types of specific impulses are given. One is ISP corresponding to sea level, and the second is ISP corresponding to vacuum. Therefore, whenever we say a rocket, somebody may give ISP at sea level, but we must be careful what he is specifying. He is specifying sea level, which is a lower value, whereas somebody may specify with respect to vacuum. Therefore, there are two ways of specifying the specific impulse, either a vacuum specific impulse or sea level specific impulse. But then there is another problem. If I have a higher value of chamber pressure, I get a higher value of expansion ratio, and I can get a higher value of the specific impulse. Therefore, I also need some terminology which says a standard, and the standard chosen is we specify specific impulse for PC equal to 7 MPa or 70 bar pressure. That means specific impulse is normally specified when the chamber pressure as a standard is equal to 70 bar, the sea level when the ambient pressure is equal to 1 bar or 100 kPa pressure. Whereas when I talk in terms of vacuum, well, I am saying that Pa is equal to 0 bar vacuum, but I still keep 70 over here. That means there are some standards, because a rocket can fire at different pressures, but if we want to compare something, we need some standard, and that standard is a chamber pressure of 70 and an ambient pressure of 1 bar for sea level ISP, and if I consider vacuum, it is there. But something to remember is, well, the vacuum specific impulse is higher than the sea level specific impulse, which is essentially Vj when the exit pressure is equal to ambient pressure. I think this is all what we have done so far, right? Are there any other questions on what we have done? If not, let me go forward. See, so far we have been talking of only one dimensional flow, right? We told ourselves, well, I need a divergent part, and I know my divergent part looks like this. I have the convergent part, but I am really not bothered about convergent, because anyway at throat I have Mach number is equal to 1. I have a chamber over here, I have PC. Now my divergent part, it is something like it is diverging out, and if I look at the flow which is taking place, the gas which is flowing near the wall will have a direction along the wall, which is flowing along the axis will have flow along the axis. Therefore, how am I justified in assuming one dimensional flow? It is really not correct. I have to make some corrections for maybe the radial flow or for the divergence in the flow. Correct? That is a simple way. That means all my thrust is not going in this direction, a component of thrust is going in this direction, it gets balanced out, and only my effective thrust in this direction, which is what is pushing me, is going to decrease. How do I get that value? Maybe let us address that in the next few minutes. Let's take a look at that. We will look at the divergent, center line, well, there is an axial flow over here. Let us assume that the half divergent angle is alpha. Now, the flow near the wall will be alpha. Maybe have to take some approximation. Maybe if I consider on an average, the flow may be alpha by 2, because here it is alpha, along the center line of symmetry it is axial. Maybe the average value of the flow, or on an average the entire flow, we can say goes through alpha by 2. I can do it rigorously, but this is sufficient for me to give an answer. In other words, on an average the flow leaves at an angle equal to alpha by 2. Is it okay? Now I tell myself, well, what is thrust? Let us assume that the nozzle is adapted, that means ambient pressure is equal to the PC here, F is equal to m dot into Vj over here. What is the mass which flows along the axis now? It is equal to m dot into cos alpha by 2, that is the axial mass flow rate, because on an average some goes at alpha, some goes at 0, the mean is at alpha by 2, the average mass is at cos alpha by 2. Vj is again corresponding to this over here, it is equal to Vj cos alpha by 2. Therefore, the thrust due to the divergence being at an angle alpha will therefore be F is equal to m dot Vj cos square alpha by 2. Please be with me. Is it all right? All what we told was the flow is not all axial, flow towards the wall is alpha, on an average the flow is at alpha by 2, and therefore the mass component along the axis is equal to m dot into cos alpha by 2, the velocity on an average axial velocity is equal to Vj cos alpha by 2, therefore the product of m dot cos alpha by 2 Vj cos alpha by 2 gives me cos square alpha by 2. Now I want to simplify this expression, therefore we use the term cos 2 theta is equal to 2 cos squared theta minus 1, or I have cos squared theta is equal to 1 plus cos 2 theta divided by 2, and therefore I can write cos square alpha by 2 is equal to 1 plus cos alpha divided by 2. Just a trigonometric manipulation, because I can express it in terms of the divergence angle, half divergence angle of the nozzle. Mind you, the total divergence is 2 alpha, I said alpha is equal to half divergence angle over here. Therefore, now I get the thrust of a nozzle F is equal to m dot Vj into 1 plus cos alpha by 2, and this is the loss due to the divergence, and therefore this is denoted by the word by the letter lambda, and we say lambda corresponds to divergence loss, or F is equal to m dot Vj into lambda, where lambda is something we say loss due to divergence. But I am really looking at a loss, see, actually I am just multiplying it by a factor. Therefore, if I have to have a loss, the loss should be something different. See, we say lambda is due to non-availability. What is not available? What is not available is delta, let us say what is not available What is not available? The thrust not available is equal to 1 minus lambda. In other words, this tells me the fraction of the availability, which we call as divergence loss factor, and if I want to put it explicitly in terms of something, the thrust which is not available, it is equal to 1 minus lambda. Therefore, I have defined two terms, and what are the two terms for the actual divergence effects? We define lambda is the divergence loss factor, or rather I have to multiply the value of m dot Vj by lambda to be able to give me the thrust. What is not available? The thrust, if everything was actual, would have been m dot Vj, therefore 1 minus lambda is not available. Therefore, I said capital delta related to the availability lambda over here. Now, why am I doing all this? I would like to still have a nozzle in which I do not have too much of this loss coming. Therefore, let us put some numbers on it. Let us put some numbers which will help us to clarify, and let us say alpha of a nozzle, could it be 0? It is not possible because I have a parallel nozzle. It could be 5 degrees alpha, it could be 10, it could be 15, it could be 20, it could be 25, let us say 30. In other words, I am looking at different nozzles for which, let us say, the divergence angle, half divergence angle varies from 0 degrees, in which case I have total effect, but it is not divergent. Therefore, this is really not a case to be considered, but let us include that. Or I have 5 degrees, 10 degrees and so on, 5 degree divergence and so on, I am varying the divergence angle. In other words, I am looking at divergence of nozzles with different angles, as it were. I want to find out, if I have these nozzles, what are the typical losses I have. Therefore, I would like to put in the value of lambda for each of these angles, and also I would like to find out what is the real loss I get. That means, this is the divergence loss coefficient and this is the loss which I have in the nozzle. I worked out these values, and let me quickly go through it, and it is quite easy to do it. You just find out the value of cos alpha. In other words, when alpha is 0, cos alpha is 1, therefore, the value of 1 plus cos alpha by 2 is 1. That means, the entire thrust is available and the loss coefficient is 0, or in terms of percentage it is 0%. When I have the value of alpha equal to 5, the value of lambda we said is 1 plus cos alpha by 2, cos alpha is around 0.99 something, and the value of lambda comes out to be 0.998, and if I have 1 minus lambda, it is equal to 0.12 percentage, that means 0.0012, it should have been actually 78 or 880 over here. Yeah, 12, correct. 0.0012, which gives 0.12%. If I have the angle as 10 degrees, it is equal to 0.9924, and the loss which comes out to be 0.76%. Let us put few more values. For 15 degrees, the value is 0.9830, 1 plus cos alpha by 2, and the loss is 1.7%. If it is 20 degrees, 0.9699, 1 minus lambda gives me a value around 3%, that is 0.97. If it is 25, it is 0.9537. I will qualify these numbers, and the loss is 4.63% or 0.0463. One last value I will put for 30 degrees, equal to 0.933, and this comes out to be 6.7%. If I were to put one more angle, let us say 35 degrees, the value is 0.9066, and the value is something like 9.04%. What is it I am doing? I am considering the divergent angle of the nozzles to vary from 5 degrees to 35 degrees. For each of the values I get the divergence coefficient, and also I am putting the loss in percentage. You find when I go for 5 degree I am losing just 0.12% thrust, for 10 degree I am losing 0.76% thrust, when I come to 15 I have lost already 1.7% thrust, when I go to 20 I am quite high, I have lost almost 3% of the thrust, when it goes to 25 it becomes 4, 6 and all that. In other words, it does not become meaningful to have any divergence angle greater than 20 degrees. In fact, if I were to compare this and this, I find that this is something like here the value is 1.75 times more, loss is 1.7 times more than if alpha were equal to 15 degrees. In other words, if the half divergent angle was 20 degrees, the loss is quite heavy here, it is something like 1.75 times more than this particular value, that is 3 divided by 1.7 is almost like 3/4, and that is 1.75 times more than this value. Therefore, the general practice therefore is let us adapt some value around 15 such that the loss is somewhat small. What loss? The divergence loss. But that is not the only reason. Let us try to put one more number onto it. Let us say I have a nozzle. I find that if I have a very small angle of 5 degrees or even 1 degree, my loss is going to be almost negligible. Therefore, why not have such a small angle? Let us see what is the implication of it. Let us say I have a nozzle center line, I have the throat radius I say is RT, the exit value is RE, and what is alpha? Alpha is the value of this angle alpha. In other words, the value of RE minus RT, which is this value, divided by the length of the divergent LD is equal to tangent of alpha, or the divergent length LD is equal to RE minus RT of cotangent of the value of alpha. Is it all right? All what we are saying is if I have a small angle nozzle, for the same exit diameter I will have a much longer one. If my angle is 0, well, my length will be infinity. Therefore, let us put the same things down over here into this plot. What do we find? Well, I just put the length of the divergent for a particular case, let us say, and since I do not want RC and RT to come in the picture, I say LD divided by RC, R at the exit RE minus radius at the throat. I find for 0 the length of the nozzle is infinity. If I have something like 5 degrees, it becomes 11.43 the particular ratio. If it is 10 degrees, it is 5.67. If it is 15 degrees, it is 3.73. If it is 20 degrees, it is 2.75. 25 it is 2.14. 30 degrees it is 1.73, and if it is 35 it is 1.43. What is it we are telling? The length of the nozzle is very large if the angle is very small, and the nozzle length reduces, but if I compare these things around 15 degree, if I compare 3.73 with 2.75, well, that change is not as rapid as it is for the smaller values. In fact, we find that it is something like 2.75 is something like 1.5 times only, and it becomes even smaller. Therefore, since the nozzle length, as it becomes longer and longer, the mass of the nozzle becomes larger, and we also told ourselves delta V, the ideal velocity of a rocket, is equal to, you have ISP or Vj ln of initial mass to the final mass of the rocket. The mass of the rocket will go up as the length of the nozzle increases, and therefore it is not good for me to go for very narrow angles, because the length of the nozzle becomes hard, the weight of the nozzle goes up, and therefore the general practice is to choose a divergence angle around 15 degrees. Mind you, it is just based on the premise that I do not lose any further, I do not lose too much of thrust here, but at the same I do not lose too much of thrust, I have lost only 1.7%, and also my nozzle weight does not go up drastically as it is if I go for smaller angle. Therefore, all what I will tell is, based on this divergence analysis, we can tell ourselves that a conical nozzle will normally have a semi divergence angle of 15 degrees. We will not go for smaller angles, because in that case the nozzle becomes long and the weight goes up. We will not go for larger values of angle, because if you go for larger angles we will lose more by the thrust as it were. Therefore, the optimum for a conical nozzle is generally kept at 15 degrees semi divergent angle. Does it make sense? Does it meaningful? Now, if this part is clear, I just have a few more things to tell in a nozzle. The question is, why did we address this divergence problem in such a critical way? Like for instance, we told ourselves, well, your nozzle is something like this, divergent, and you are interested in this angle being alpha, you do not want to lose thrust. What prevents us from having a nozzle which I can bring it back like this, I can initially expand it out and bring it like this? What am I talking? Let me make myself a little more clearer. We have the throat here, I have a conical nozzle. If I have the divergence angle alpha, and the divergence angle at the exit is important, and if I can somehow reduce this divergence angle over here, and in the initial stages what I do is I expand it like this and bring it back like this. That means I expand it out and bring it like this, or the shape looks something like a bell. The shape of the nozzle looks like a bell here. I am sorry, the figure is not all right. This is the center line. How does a bell look like? Like this. Initially I expand it out, I decrease the divergence angle such that the flow goes out more axially. In other words, I have a contour for this shape, and these are known as contour nozzles. Or simply stated, bell nozzle. I think I have to spend a couple of minutes on this. Let's try to find out what exactly is the role of this. Why did I say initially you expand out the gases? Let's plot out the pressure distribution in a nozzle, because we now know how to do it. We told ourselves the pressure at the throat is equal to 2 over gamma plus 1 divided by, we had an expression, gamma by gamma minus 1. Let's do that. Chamber, center line, we have the nozzle convergent, I have a conical nozzle. Let us say the angle is still meaningful, let us say around 15 degrees. I do a one dimensional analysis. This is the throat. I plot the value of pressure in the nozzle as a function of distance over here. This is from the chamber, this is at the throat T, and you have the divergence over here at the exit over here. Okay. Now what will the pressure be from the chamber pressure? The pressure keeps falling, let us say this is the chamber pressure value. At the throat it is, you know how to calculate 2 over gamma plus 1 into gamma by gamma minus 1, the pressure keeps falling like this, and this is the exit value of pressure, right. Okay. This is for a conical nozzle. All what I am trying to say is, in this part the pressure is still quite high, therefore over here maybe I slightly, what I do is I expand the gases a little bit more, because the pressure is high, the flow cannot separate, it has to follow the wall, and then I reclaim it and bring it back over here. In other words, over here I expand the gases at higher pressure and then I bring it over here, in which case it will be possible for me even to reduce the length of the nozzle, and therefore these bell nozzles are specified in terms of, let us say 80% bell, or they say 70% bell. What do we mean? A bell nozzle whose length is 80% of a conical nozzle is all what is required. I can terminate this over here, because here itself I have got the value of P, and therefore I am able to use a conical nozzle or a contour nozzle much more effectively than a bell nozzle, than a conical nozzle. In other words, a bell nozzle I can give a divergence angle between, let us say 2 degrees to something like 5 degrees. Initially I expand it rapidly, here I give a large value, maybe 20 degrees to 50 degrees, and in the process I can make the nozzle a little more stubby, and I tell that the length of the bell nozzle could be a fraction of this, and this is what we call as a bell nozzle. 80% bell nozzle means the length of the bell nozzle is 0.8 times that of a conical nozzle. What do we do in a bell nozzle? We immediately expand downstream of the throat, allow the divergence to be smaller such that I lose less by nature of the divergence loss. In fact, one paper which all of us must read is by, I will give you that paper here, it is very important. It was first put forward in Rocket Dyne, I think, and this particular person who worked on it is an Indian by name G.V.R. Rao. It is known, bell nozzle is also known as Rao's nozzle, it is known as exhaust nozzle, contour for optimum thrust. This came in a journal known as Jet Propulsion, which preceded the AAA journal, volume number 138, no, volume 38, I am sorry, 1958. The page is 377 to I think 381. Please, if you all have some time, please go through this. You know, all what is done is, if you want to work out in detail what is happening in a bell nozzle is, you expand the gas rapidly, you have something like expansion, and then you have compression, it compresses the flow and comes over here. With the result, I can afford to have a shorter nozzle compared to a conical nozzle, which is a bell nozzle. And most rockets make use of bell nozzles. And if I have a bell nozzle, none of the earlier criterion like flow separation and all are possible, because I am having higher pressure gradient along the wall. Therefore, whenever we talk of Summerfield criterion saying exit pressure is 0.4 times the ambient, it is more applicable for conical nozzles and not for bell nozzle. I think this is all about nozzles, conical nozzle, maybe the contour nozzle. I want to spend another few minutes on different types of nozzles. Can we have different types of nozzles? Something which I would like to say is Is it possible to have a different type of nozzle altogether? A nozzle we say has to adapt to altitude. That means can I make it adapt to different altitudes, start from 0 kilometers and keep going up to 10 kilometers or 100 kilometers for the same nozzle? And maybe some of these things I will do in the next class. Maybe just spend 5 to 10 minutes on different types of nozzles and work out 1 or 2 small problems. Well, thank you then. I think that is about it.